The topic in this video is transformers, so we'll start off with this, something to think about. As you watch this, you're going to need to take some notes on it, and when I tell you to pause, I would really strongly suggest you pause and do the things I ask you to do. So let's start with this question: where are some places you see transformers in your everyday life? So here's our first pause. Take a pause and think about where you do see transformers in your life. Okay, so hopefully you've identified some places where you see transformers. There may be one in your yard, there may be one on a pole behind your house. You may see transformer stations on the way to school, or maybe you drive past them on the road or in town. Sometimes there's transformer stations. So you may have seen transformers around. If not, I do have some pictures coming up here. So our objective today is to learn about transformers. Here are a couple of kind of transformers you might have seen. This kind of transformer you find hanging, as it shows here, on a pole back behind your house. And for example, places I've lived, 4 houses are connected to one of these transformers. And then maybe you see these kind of transformers as well that are on the ground. They're much larger. They probably have some fairly large lines coming into them and some kind of structure like this around it. And they're probably in a barbed wire, or at least a cyclone fence enclosure with the barbed wire top on it, because it's very dangerous in here. The voltages and currents flowing through here are very high. All right, so these are some things you might have seen now, so you have an idea what we're talking about. They are both examples of transformers, and a transformer is called that because it's used to change the voltage and the current in AC circuits. And it's important to remember these work only in AC circuits. If you have a DC circuit, you cannot use a transformer for reasons that we'll see here in a second. Okay, so if we have a coil of wire and the current is changing, while the current's changing, the magnetic field is changing as well, because remember, current-bearing wires have a magnetic field around them. So if we change the current, we change the magnetic field. So if the current's increasing, the magnetic field increases along with it, and likewise the opposite would occur. The field decreases as the current decreases, and if we don't have a change in the current, then the magnetic field is steady in one place. So I used this graphic before. It's an electromagnet. All right, so if we are feeding the current into it in a steady state, so it's just coming in here, we wouldn't get this kind of moving magnetic field. If, however, we increase the rate of current, then the field will get bigger. If we decrease it, the field will get smaller, so it decreases. If we change it constantly, the field will constantly be changing size as well. Okay, so we can take advantage of that. So here we have 2 coils. Here's a coil of wire that's hooked up to a power supply, and then here's a coil of wire that's hooked up to something else. We don't know what it is. All right, so if we did this, if we hooked this up to a, let's just make it a DC power supply, and then we close a switch across here, then as the current begins to flow through this coil, the magnetic field, which is at 0, will begin to grow, and as it grows, it will grow in loops. And those loops will get bigger and bigger, and as they get bigger, they will move across this wire and induce voltage across this coil. And so we can actually get something that seems kind of strange, that as we close this switch, we'll suddenly get current in this coil for a brief moment. Now, only because while the field is changing, while the current is changing, this field gets bigger and crosses over the coils here, and while the coils are being cut, then voltage is being induced. Once the field reaches a steady state, then this all stops. So what we would do is something like this. If we just go ahead and close this switch and this power supply, make it AC. So now the current is changing every half turn of the generator. So over here in this coil, the field will grow big and cross over this coil and then collapse and grow big in the opposite direction, crossing over this coil again and collapsing. So every half turn, field grows and collapses, and it induces a current and a voltage in this coil at the same rate it is over here. So we'll actually get transfer of energy without touching here, and that's how a transformer works. So as it says here, the changing magnetic field of the first coil will induce EMF in the second coil. All right, so a transformer works on that same principle. Here are 2 coils. Sorry, here we go. 2 coils, the primary coil and the secondary coil. The rule is the primary coil is the one that's hooked up to the source of EMF, and the secondary is hooked up to the load. So here comes the current in to the primary, and our source would be AC. The field will grow and collapse across this coil. It will cross over this coil and induce EMF in this coil, and so we will get a transfer of energy across this transformer. Right now, how is that going to work, and why do we have this set up the way we do? Well, here's that same picture. EMF is BLV, which we learned previously. That's magnetic field, length of wire, and the speed with which that wire moves through the magnetic field perpendicular to it. For this, the B, the magnetic field, is the same for both. They're both experiencing the same magnetic field, and the speed with which the field grows and collapses is the same for both of them. That doesn't change. So the EMF depends only on L, the length of coil. So in this particular one, we're going to count how many of these are, they'll call them turns of the transformer. So how many turns there are on the primary and how many turns there are on the secondary will determine it. So if you look at this one, let me grab that out of the way again. The primary has 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. The secondary has 1, 2, 3, 4, 5, 6. So more EMF in this side than there will be in this side, so because there's more coils on this side or more turns. All right, so here's another picture, one from a textbook. This is the primary side, 2 turns. Here's the secondary side, 4 turns. N refers to the number of turns. Okay, so number of turns is 2 to 4. So what's going to happen in this one is because there's 4 over here and only 2 over there, we will get twice as much EMF on this side as we do on this side because the length of wire in the field is doubled. All right. So this is really an easy math problem. So VP is the potential or the EMF in the primary side, N is the number of coils or turns in the primary side, and that has to be equal to the voltage on the secondary side divided by the number of turns on the secondary side. So it's just a proportion, simple proportion. So as the number of turns goes up, the voltage will go up, and as the number of turns goes down, the voltage goes down. All right, so we have 2 different ways we can use transformers. We can use them to step up the voltage, or we can use them to step down the voltage. All right, so if we have a step-up transformer, is one that increases the EMF. So the coil configuration, well, I'm going to pause this, and I'm going to let you think about what the coil configurations will be for each of these situations for a step-up transformer and a step-down transformer. Okay, we've looked at both a step-up and a step-down transformer already here. Let's back up. Which one is this? Well, this is a step-up transformer. Fewer on the primary side, more on the secondary side. This is a step-down transformer. More turns on the primary side, fewer on the secondary side. All right, so hopefully you got that figured out. All right, now, how is it possible that the step-up transformer can increase V? Aren't we getting something for nothing, as the saying goes? And the answer to that is no, in fact, we're not. The power produced and sent into the transformer is equal to VI, this equation we've used before. So if it is an ideal transformer, we make the assumption that it is, even though that's a pretty bad assumption. That is, the power put into the primary is equal to the power on the secondary side. If we assume it's ideal, then V of the primary side times I of the primary side equals the same thing for the secondary side, which means if we rearrange it, that we get this, which looks at first like a proportion, but look at it again. It's VP to VS equals IS to IP. In other words, when voltages go up, currents go down. We can also see that from this one as well. When the voltage is increased, the current is decreased. So a step-up transformer can increase V because it lowers I. We've actually talked about this in the past in transmitting electric power. All right, so a step-up transformer increases the voltage but decreases the current, and a step-down transformer decreases the voltage, increasing the current. Now let's look at why we'd need to do that. This is not a very practical application, but go ahead and have a look here. Here is a source of potential, let's assume it's AC, hooked directly to one wire, or one set of wires hooked directly to a bulb, and then another set of wires going to a transformer hooked to another set of bulb. So the question is, another bulb, I'm sorry. What can you say about the two lamps in the diagram? So pause it here and think about that. Okay, so hopefully what we realize here is that this one gets the voltage directly from the source, and so it'll light up with some brightness. But this one's on a step-up transformer. Fewer coils, more coils. Step-up transformer means more voltage. The resistance in the lamp is the same, so if there's more voltage with the same resistance, there's more current. This one will glow brighter. All right. Now, we talked about this before, so let's just kind of review this. We generally don't want power plants near us. As you can see from this one, this is a power plant in another country. It's a little misleading too. It is a coal-fired power plant, which we can tell because there are smokestacks. But then these things, which we associate in the United States with nuclear power plants, these are just cooling towers. They're just there to cool off the hot water that you use for the power plant. So it's got nothing to do with nuclear. So they're giving off gas out of the smokestacks. They give off heat. They make noise. If they're nuclear plants, they could potentially give off radioactivity. We want them far away. And so we have the problem of transmitting the power, again, we talked about this before, over high lines like this. And so this is what transformers are going to do for us. We transmit electricity long distances through wires. We get the wire to have as good quality as possible. The power loss is that I squared R loss. Again, we've been through this. So we decrease power loss. Okay, so I take a moment now and pause and think about this and review. So you've got this in your notes somewhere, how we decrease power loss we talked about in the last test. So let's look here. This is an interesting little graphic produced by the Occupational Safety and Health Administration on their website. And so it shows how, in this graphic, here's the power generator. Out of the generator comes a 20,000 volt potential. And then that is transformed at a step-up transformer substation up to 345,000 volts. It's distributed then. So maybe it goes to a step-down transformer at an industrial plant. Somebody's going to use a lot of electricity, so they're going to send that in at a high voltage because maybe they got equipment that runs on high voltages. And then you're going to send it on. You're going to start stepping it down as you get near a city so you don't have such high voltage running through the power lines in the city. Maybe to an industrial customer that uses 440 volts, or you send it overhead to another distributor substation. So here is maybe like a retail business that maybe needs 220 or 440 volts. Here's somebody who runs on regular standard household current, or here's an actual house. And so into these things are sent 120 or 240 volts using transformers on the poles. And then here's the more modern way of doing it, which is you have a transformer on or in the ground, and then you send it to the house, and in the house or the business, this is a business, then you send it the 120 or 240. And I don't know, we talked about this maybe already, that they send 240 into your house and then they just split it. So when you need 120, like to plug in your hair dryer or your cell phone, then they just split the 240 in half and use one half of it. Okay, so there is the use of transformers. This is actually a nice website. Let me go back up so you can see the web address up here that gives you some information on how electricity is produced and how it's transmitted.